Welcome back to the Deep Dive, the show where we take that fire hose of information you've shared with us, all the articles, the research, the docs, and really try to turn it into something, usable.
And today, we're making a pretty significant turn, I think. If our last deep dive was all about the blueprint, drawing that perfect architecture for the backup system.
The clean schematic, the servers, the storage targets, all of it.
Exactly. Today, we are stepping into the real world. We're shifting focus from that neat and tidy data center diagram to the chaos of managing thousands of actual data sources.
The clients.
The clients, all of them.
Okay, let's really get into this because it's a huge task. We know the backbone is solid, but in any real enterprise, the challenge isn't just designing a perfect vault. It's managing all the uniquely difficult, non-standard doors that lead into it.
That's a great way to put it.
And that vast,
Yeah.
what the sources call heterogeneity of the client environment. That's really the driver of all the complexity, isn't it?
Yeah, it is. The servers, the databases, the laptops, all running different operating systems. It's the #1 cause of failures.
So our mission today is to really distill the key technical points and, maybe more importantly, the painful logistical challenges that you see in client-side data protection. We're focusing on how these different clients, often against our best intentions, just break the rules.
Precisely. For you listening, the goal is to synthesize all this fragmented knowledge. How do you deal with a massive Oracle database that needs, say, 4 concurrent streams, and at the same time, 1,000 sales laptops that are only on the network for an hour a day?
A balancing act.
It is. So we've structured this deep dive into 4 main areas. We'll start with the core planning fundamentals. Then we'll get into specific strategies for scaling up to handle the really large and complex clients.
Okay.
After that, we'll tackle the geographic and mobile puzzle, which, well, it's only getting messier. And finally, we'll do a really deep analysis of performance bottlenecks, especially those nasty little network gremlins that just destroy your backup windows.
All right, let's lay that groundwork. The fundamentals. The sources we have really emphasize that this all starts way before you even install an agent. It's about matching the client's characteristics.
It's data type, its size.
It's business criticality, right? Matching all of that to the features of your backup application. It's an alignment exercise from the get-go.
It absolutely is. You have to figure out the commonality of that data first. How often does it change? Is it structured, unstructured? Is it already compressed at the source?
And what kind of application is running on it?
Yes, that's huge. If a client is running a highly transactional database, your backup solution needs an application-specific integration, an agent, an API, something that guarantees consistency.
You can't just stun the database and hope for the best.
No, you'll get a corrupt, useless backup. But if it's just a simple file share, a standard file system agent might be perfectly fine. If you get this initial alignment wrong, the best architecture in the world is not going to save you.
And all of that, every technical decision, is ultimately driven by the business needs. Which brings us right back to service level objectives, or SLOs. We can't talk about this enough.
The SLOs are the engine. They drive all of this planning. We really focus on 2 critical metrics: the recovery point objective, RPO, and the recovery time objective, RTO.
Let's break those down. RPO is about data loss.
Right. The RPO dictates the maximum amount of data loss the business can tolerate. It's usually measured in time, let's say 4 hours.
Okay.
If the RPO is 4 hours, your backup or your replica must complete within that window. So if a critical backup job starts at 10 p.m. and it finishes at 4:05 a.m., and then that database fails at 4:30 a.m., you've already violated your 4-hour RPO.
Wow, okay, so the calculation isn't just how often should I run the backup, it's actually how fast must this backup finish.
Precisely. That one simple constraint dictates your entire architecture. You have to plan the minimum frequency and the maximum allowed transfer time, all based on that RPO.
And this is where that heterogeneity you mentioned really kicks in, because not all data is created equal.
Not at all. A company's main ERP database might need a 2-hour RPO. The public relations file share. Maybe they can tolerate a 24-hour RPO. You have to tier your objectives and then allocate resources, bandwidth, processing power to make sure the high-priority jobs always succeed.
And the RPO also helps set the longer-term goal, the retention policy.
Correct. The retention policy has to meet not just that operational RPO for, yesterday's file, but also any long-term regulatory or legal requirements.
So you have 2 competing needs.
Exactly. The most common restore request is, I accidentally deleted a file yesterday. That only requires maybe a few weeks of backups on hand. But then you have regulations, like for financial records, that might demand you keep monthly backups for 7 or 10 years.
That's a huge difference in storage needs.
It's massive, and that dichotomy, short-term operational need versus long-term compliance, is what guides your capacity planning and even your choice of storage media. Fast disk for the short-term stuff, chip or tape, or cloud archive for the long-term.
Okay, so once we understand the what and the when, the name of the game is efficiency. How do we start organizing this zoo of diverse clients?
The foundational rule from all the source material is keep it simple and standardized.
Easier said than done.
Oh, absolutely. But standard configurations drastically decrease your administrative risk and they increase resource utilization. The main tool for this is group configuration.
So how do we define a group? What are the criteria?
A group is just a collection of clients with shared attributes. So similar data sets, similar schedules like daily incrementals, and similar retention requirements.
For example?
If you have 5 web servers, all running the same OS, all serving the same function, they should absolutely be in the same backup group. This just minimizes your overhead. You define the policy once for the group, not 5 times for each server.
But I can already see the problem. You can't force standardization onto highly specialized systems. That's where it breaks down, right?
That's the big caveat. You're right. You almost always need separate custom groups for specific workloads that just don't fit the standard mold.
Like databases.
Databases are the classic example. They need application-aware agents to freeze transactions correctly. Or think about massive NAS systems that need specialized NDMP protocols. You can't just lump those in with the file server.
Or what about geography?
That's another big one. Clients in different time zones, we'll get into that more later, but they demand their own groups simply because their backup window is shifted. If you try to shoehorn an Oracle database into your standard file server group, you're just asking for an inconsistent, unrecoverable backup.
That makes perfect sense. So let's zoom in a little bit from the group to inside a single client. Let's talk about dataset definition and granularity. This is where we get surgical.
Exactly. You might have one server with, say, 15 terabytes of storage, but that storage isn't all the same. Maybe 13 terabytes of that is static, archival data, and 2 terabytes is highly transactional, active user data.
So you define separate datasets within that one client.
You have to. The 2 terabyte active data set gets the high-frequency 4-hour RPO treatment, the 13 terabyte archive. That can get a slower, maybe monthly, full backup.
And this is often necessary because the sheer volume of data prevents a single backup from finishing in time. The sources call them a single save set backup.
Correct. A save set is the technical term for that logical collection of data being backed up in one operation. So you segment that save set definition to work around your resource constraints. If you don't have enough memory or LAN bandwidth to back up all 15 terabytes at once, breaking it into smaller, manageable save sets is the tactical solution.
And this granularity has a huge impact on the other side of the coin, recovery.
It ties directly into the recovery time objective, the RTO. If your RTO demands that you can recover a single file in, say, 5 minutes, you need file-level granularity in your backup.
Which is the most common restore request.
Right.
A single file or a folder, not a full system rebuild.
It is, by far. Now, you could opt for a raw device-level backup. It's really fast for the backup itself because it bypasses all the file system overhead. But then you sacrifice that granularity. To restore a single file from a raw backup, you have to restore the entire raw volume first, then mount it, then find the file. It massively inflates your RTO and your resource consumption. So planning your granularity upfront is absolutely non-negotiable if you want to meet your RTOs.
All right, we've got the fundamentals down. Now let's tackle the real scaling challenge. The clients that are just too big, too complex, or whose size just breaks that conventional single-stream backup logic?
Yeah, the single-thread sequential backup model it's basically obsolete in a modern data center. If you have a multi-terabyte system, relying on one massive sequential data stream is just asking for trouble.
It's inefficient and it's fragile.
Incredibly fragile. If that one connection drops and the backup window closes 5 minutes before it's done, you have to start all over again.
So the technical solution that's heavily emphasized in the sources is multi-streaming.
Multi-streaming is all about parallelism. It's the process of sending multiple simultaneous backup jobs or distinct data streams from a single client.
And this is enabled by the application itself.
Either by the application, think of enterprise databases like Oracle, which let you specify parallel channels to dump data, or by protocols like NDMP, the Network Data Management Protocol, which is used for NAS devices.
So instead of one 200-gigabyte file going sequentially.
You might configure 4 concurrent streams, each one handling 50 gigs of that file. It gets the job done much, much faster.
So how do you figure out the right number of streams? Is more always better?
No, more is definitely not always better. This is a common mistake. You have to match the number of streams to the capabilities of your backup target, your storage device.
Okay, explain that.
Well, if your storage node is only connected to, say, 2 physical tape drives, or maybe your deduplication appliance is licensed for only 4 concurrent ingest processes,
Okay. Then running 8 streams from the client doesn't help.
it hurts. You're just overwhelming the target. The excess streams will either queue up or fail outright. You end up creating an artificial bottleneck at the storage layer. The best practice is always to tune the client's parallelism to maximize the target's capacity without overloading it.
So you're optimizing the producer, the client, to match the consumer, the storage node. Makes sense. Now, beyond just parallel data flow, what about load distribution for a client that's just overwhelmingly large in total size?
For that, you use job segmentation and staggering. Let's say a single client has a 30 terabyte save set that takes 12 hours to back up, but you only have an 8-hour window.
You're stuck.
Unless you break that massive save set into multiple, smaller, separate save sets, maybe one job for the C drive, one for the application partition, and then 3 more for the user data volumes, you segment the work.
And the staggering part.
Once they're segmented, you stagger their start times. Instead of kicking off all 5 massive jobs at 10 p.m. and creating this huge surge of network traffic that could choke the switch.
You spread it out.
Exactly. You start job 1 at 10 p.m., job 2 at 11:30, and so on. You distribute the load evenly over the entire backup window. This gives you predictable network use and prevents resource contention across the whole infrastructure.
This all sounds like we're managing the symptoms of having too much data. The ideal solution, though, would be to avoid backing up the data in the first place by reducing the data footprint at the source.
That is the most elegant solution because you solve the scaling problem without buying more hardware or more throughput. The source material highlights 2 main ways to do this. First is using deduplication technology.
Specifically, source-based deduplication.
Yes, source-based. And there's a really important trade-off here.
Source-based dedupe is incredibly efficient for the network, but it costs the client something, doesn't it?
It costs the client CPU and memory, a lot of it. Source-based dedupe finds and eliminates redundant data on the client machine itself before anything is sent over the wire. It calculates hashes of data blocks and only sends the unique ones.
Which is transformative for bandwidth, especially over a slow one.
Oh, it's a game changer. But the client's CPU and memory have to do all that work. The chunking, the hashing, the lookups. It's computationally expensive. You are effectively shifting the bottleneck from the network pipe to the client's own resources.
So if I have a client that's already running at 95 per CPU doing his production job, and I turn on source-based dedupe,
You might solve your network problem but cause a local performance crisis. The primary application could grind to a halt.
so you have to ensure the client has enough headroom, enough spare CPU cores and RAM to handle the dedupe process without impacting its real job.
It's a critical architectural trade-off that people frequently overlook.
Okay, so that's one method of reduction. What's the second?
The second is much simpler, conceptually. It's archiving old or non-active data. It's just good data lifecycle management. If a file hasn't been accessed in 2 years, move it off the expensive, high-performance production system and onto a cheaper, separate archive repository.
And that shrinks your backup window.
Drastically. You reduce the volume of data that needs to be backed up every single night. Your daily backups become lean and fast because they're only protecting the active, changing data.
The sources also mention something that feels like a pretty radical idea, converting clients into storage nodes. That seems like decentralization in its purest form.
It is. By converting a client machine into a storage node, you're changing its role. It goes from being a data source that sends data over the LAN to a data processor that can receive or store data locally.
Where would that be most useful?
It's particularly useful in big distributed environments like remote offices. Instead of having a central backup server in the main data center, pull all the data from a branch office across a slow WAN link.
The local machine acts as its own backup appliance.
Right. It writes directly to local disk or maybe a small tape library in that office. This localizes all the processing and storage I/O, and it drastically reduces the strain on the central backup server and the corporate network.
Of course, the simplest strategy of all is still just backing up only what's changed.
Absolutely. Reducing the frequency of full backups is key, as long as your RTO and RPO allow for it. Full backups are resource hogs. Incremental or differential backups, which only capture changes, are significantly faster and should really be the backbone of your daily schedule.
But there's a balance to be struck there, too.
There is. If you run too few full backups, your recovery process becomes slower and more complex because you have to stitch together a full and many incrementals. But if you run too many, you risk violating your backup window. It's always a trade-off.
Okay, let's shift gears to a really counterintuitive performance killer, the small file dilemma. It sounds absurd, but why does backing up 1 terabyte of millions of tiny files take so much longer than backing up 1 terabyte from just a few huge files?
This is a critical point that trips up so many administrators. The total byte count is completely misleading. The bottleneck isn't the data transfer rate at all, it's the administrative I/O overhead.
What do you mean by administrative overhead?
I mean, the backup process has to interact with the operating system so intensely. We're talking about hundreds of thousands, sometimes millions of individual system calls
For each file?
for each tiny file. Each one requires a separate request to get its metadata, check permissions, make an open file call. The CPU is just drowning in this administrative handshaking and traversing the file system tree.
And what about the backup applications catalog?
That's the other part of it. The catalog operation, the indexing and lookup process the backup app uses to track where every file is incredibly intensive, and it has to do it for every single one of those small files.
So the CPU is basically stalled doing clerical work instead of actually pushing data.
That's a perfect way to describe it. The sheer volume of these individual operations creates massive I/O overhead and increases the seek time on the client's disk. This is a notorious performance killer in environments with tons of small files, like user home directories or virtual machine repositories.
So how do specialized tools get around this administrative drain?
The materials point to specialized tech, sometimes called SnapImage or something similar, that uses block tracking. This provides a necessary layer of abstraction.
So it's not looking at files anymore.
Right. Instead of relying on those slow file-by-file system calls and index lookups, block tracking monitors the storage blocks themselves down at the volume level. When a change happens, the system just records the changed block address, not the changed file name.
So it's much more efficient.
Massively. It shifts the entire backup process from the inefficient file system level to the much, much more efficient disk block level. This drastically reduces that overhead we were talking about. It's pretty much essential for environments with very high file counts.
Okay, we've figured out the rules for the big static servers in the data center. Now we have to move to the logistical nightmare of the modern enterprise. Data that's mobile, geographically dispersed, and often turned off when you need it most. This starts with desktop and laptop backup challenges.
Right. Unlike your production servers, which are hopefully running 24/7 in a nice climate-controlled room, desktops and laptops are the definition of non-standard and transient.
And the number one problem is the backup window conflict. Servers get backed up at night when activity is low. Laptops are, well, they're at home, asleep, or disconnected during that window.
Precisely. They have to be backed up during the business day when the user is connected and actively working. And that means the backup runs at the same time as production work.
Which can impact performance.
If that traffic isn't managed very, very carefully, if it consumes too much LAN bandwidth or CPU on the machine, it slows down the user's applications. It can even impact other production systems sharing the network. This forces IT teams to use really sophisticated scheduling, tools that only run backups when network congestion is below a certain threshold.
And for these endpoints, we need a totally different approach to capacity management compared to servers. We can't just back up the whole C drive every time.
No, you have to be ruthless in what you choose to protect. The focus has to be only on the user files, their folders, and maybe some critical profile settings. You must deliberately exclude all the common reproducible data.
Like the operating system files.
The OS, the application executables, cached internet files, temp files, all the stuff that can be easily reinstalled from a standard corporate image.
But that requires a lot of configuration.
It does. It requires meticulous configuration of exclusion lists, which itself becomes a massive administrative burden when you're dealing with thousands of non-standard machines. The goal is to protect only the irreplaceable work files.
So if a company has thousands of these mobile clients, how do they handle that administrative and connection load?
Well, standardization through grouping is still crucial. You use single backup groups for large numbers of clients in the same area to standardize the policies. But more importantly, scale demands decentralization.
How do you mean?
If you have a significant number of clients in one location, say a branch office with 500 laptops, you should always consider putting a dedicated local storage node or even a small backup server in that
To
office.
keep the traffic local.
Exactly. It localizes all the backup activity, preventing 500 individual data streams from hammering the central data center over the WAN all at the same time.
That leads us directly to the next layer of complexity, clients in different time zones.
This is a huge operational clash. Imagine your central backup facility is in New York, and its optimal processing window is, say, 10 p.m. to 6 a.m. Eastern Time.
Okay.
But you have a big branch office in London. They're 5 hours ahead. Their optimal window, their local nighttime, is right in the middle of New York's business day.
So their best time to back up is when the central server is at its busiest, handling production tasks or recovery requests.
It creates completely unnecessary contention. The solution, again, is localization and then replication. You back up the time zone separated clients to a dedicated local storage node in their region.
So the data is protected locally during their off-peak hours.
Right. RPO is met locally without any drama. Then that local node can replicate the data, often deduplicated to save bandwidth to the central site during an agreed-upon non-peak window that works for both locations. It buffers that time zone clash.
This problem gets even worse when we look at remote location challenges in distributed environments, thinking about like hundreds of retail branches or banks where the physical network connection is really weak.
This is where traditional backup applications just fall apart spectacularly. The primary challenge is the bandwidth problem. Remote offices often rely on these narrow pipes, T1 lines, shared WAN connections with limited bandwidth.
And traditional backups send a lot of data.
They send huge chunks of raw data, and that saturates the pipe almost instantly.
What's the consequence of that, beyond just being slow?
Well, the sources note that the narrower the pipe, the slower the completion time, which means violating your RPO becomes almost inevitable. But even worse, the high utilization increases the chance of network congestion, dropped packets, and session timeouts.
So the backups just fail.
They fail, and they have to be manually restarted. It's a massive operational cost. That narrow pipe makes the entire operation incredibly fragile.
This is really the use case that justifies the cost of technologies like source-based deduplication.
Oh, absolutely. Deduplication completely transforms remote backup. It changes it from a data transfer problem into a metadata transfer problem. Because only the unique changed blocks have to travel across the WAN, you can get bandwidth efficiency of, up to 99%.
It's an operation that would vanish in hours.
Can often complete in minutes. It's absolutely essential for managing data growth in remote offices with limited connectivity.
And finally, protecting data at these remote sites introduces some significant security concerns.
When data leaves the controlled environment of the central data center and travels across public or shared networks, even encrypted WAN links, it just faces higher security risks.
So you need more protection.
You do. It mandates that you address security rigorously, particularly with end-to-end encryption. The data stream has to be protected in flight, either by the backup agent itself using client-side encryption or by a secure transport protocol because it's now exposed to a much wider, less controlled network.
Okay, so we've moved data from the server across time zones, dealt with bad bandwidth. Now we need to look under the hood, because often the bottleneck isn't the distance or the connection speed, it's the client itself or some subtle flaw in the network. Let's start with client-side performance impacts.
The backup process is a resource hog. There's no way around it. It requires significant CPU, I/O, and memory. The application has to read data from the disk, which is I/O, process it, that's CPU for compression or encryption, and hold it in memory before sending it out.
So if the client is already constrained,
If it's already running at 90% CPU, just doing its normal job, the backup process will slow to a crawl. It simply can't generate the data stream fast enough to feed the network.
and what happens when a machine is starved for memory during a backup?
It leads to that dreaded resource degradation we call swapping or paging. The operating system starts moving active memory pages out of physical RAM and onto the disk's swap file.
And disk is thousands of times slower than RAM.
Exponentially slower. So the backup application's threads just grind to a halt, waiting for necessary instructions or data buffers to be read back from that slow swap file. The solution is to make sure there's enough free memory during the backup, or to configure a very large page file so the app has room to breathe without stalling the whole system.
This problem is magnified dramatically in virtual environments. Let's talk about virtualization stress.
This is the shared resource curse. In a virtualized environment, if you try to back up, say, 10 guest machines on a single ESX hypervisor at the same time, you immediately hit severe throughput limits.
Because they're all fighting for the same hardware?
All fighting for the same limited pool of physical CPU cores, the same memory modules, and the same host I/O capacity. Backing up all 10 at once degrades the performance of every single one, and you often see slow application response times on the guests themselves.
So how do we get that processing strain off the hypervisor host?
We use technologies like VMware's VADP, the vStorage APIs for data protection, and we use proxy servers. VADP lets the backup application bypass the guest operating system entirely.
So no agent inside the virtual machine.
Right. Instead, the backup server initiates a snapshot of the virtual disk at the hypervisor level. That snapshot is then mounted by a dedicated separate machine called a proxy server.
And the proxy server does all the heavy lifting.
Exactly. The proxy has its own dedicated CPU and memory, and it handles all the data processing, the deduplication, the movement to backup storage. It completely removes the I/O and CPU burden from that high-stress ESX host. That separation is essential for scaling in virtual environments.
Going back to the disk itself for a moment. We talked about small files, but the physical state of the client's disk also matters. Let's touch on fragmentation and seek time.
While fragmentation is definitely less of a concern on modern SSDs, it's still a critical factor for any environment with spinning hard disks or poorly managed virtual disks. High file system fragmentation means the client's redhead has to physically jump all over the disk platters to gather all the data blocks for a single save set.
Lots of wasted motion.
A ton of wasted motion. It performs all these excessive seek operations, which dramatically increases the seek time and delays the start of the data transfer. It can waste minutes of a very tight backup window. A defragmented volume can read that data sequentially much, much faster.
Okay, the client is optimized. The data is ready to hit the wires. Let's talk about the paradox of the network performance and design considerations. We need to clarify the difference between theoretical speed and what's actually available.
Right. The network speed is what's advertised 10 GBps, for example, but the effective performance, the actual throughput you get, is almost always lower.
Why is that?
It's because LANs rely on the TCP/IP protocol stack, which introduces a significant amount of overhead. TCP/IP was originally designed for resilient communication using small blocks of data, not for sustained, high-speed streaming of massive backup save sets. All the necessary handshakes, acknowledgments, and error checking in TCP/IP consume a large chunk of that theoretical bandwidth.
So if your backup traffic is competing with production traffic on the same network, you have a huge problem.
A major problem. The time-tested strategy to mitigate this is separating the traffic. You build a dedicated backup LAN, often using high-speed GG or even fiber channel that is used strictly for backup traffic.
So the heavy data movement doesn't congest the production network.
Exactly. It ensures backup I/O doesn't starve production I/O. If building a whole separate network is too expensive, you can sometimes use an existing management LAN as long as it's physically separate from the main data path. The key is insulation.
And the sources introduce a piece of hardware designed specifically to fight that TCP/IP overhead.
Yes, the TCP offload engine, or TOE card. You can think of a TOE card as giving your backup stream its own dedicated border guard. It's a specialized network interface card, an NIC, with its own onboard processor.
And that processor's job.
Its job is to offload the burden of managing all the low-level TCP/IP protocols, the handshakes, the sequencing, the packet assembly from the host's main CPU.
That's a great metaphor. So the host CPU is freed up to do its real job.
Precisely. And network performance improves because that dedicated TOE processor is handling all the protocol complexity, allowing the host to just push data payloads more efficiently. It maximizes your throughput while minimizing resource use on the client. It's a vital piece of the puzzle for intense backup environments.
But even with separated high-speed networks and TOE cards, we can still face that insidious invisible killer, the latency problem.
Latency is that unavoidable time delay in any IP network. It's the time it takes for a packet to travel from the sender to the receiver and for an acknowledgement to come back. And while distance causes some of it, the most significant source by far is network congestion. If the physical path is overloaded, packets get queued up, and that leads to unacceptable delays.
Physical problems. Like a damaged cable.
A kinked network cable, a faulty patch panel, signal degradation over a run that's too long, all of those will cause intermittent packet loss. And when packets are lost, the system has to trigger the most severe performance killer of all, TCP retransmissions.
Let's really drill into retransmissions. Why are they so destructive to the backup data rate?
A retransmission happens when the sending machine fails to get an acknowledgement, an ACK, for a packet it sent within a specific timeout period. The sender then assumes the packet was lost. It has to pause its transmission entirely, wait, and then resend the data.
So it's all stop and go.
It's pure stop and go, and it absolutely destroys throughput. A connection that should be running at 100 megabytes per second might suddenly drop to 5 megabytes per second if retransmissions spike. When you're troubleshooting a slow backup, a high retransmission rate is the smoking gun.
So what causes this packet loss, besides just general congestion?
It could be buffer overflows on the receiving device, physical link errors, but the most common and most difficult to diagnose culprit in the enterprise is the duplex mismatch.
This is a crucial detail. Explain what a duplex mismatch is and why it's so catastrophic for performance.
A duplex mismatch happens when two devices on a network link have incompatible speed or duplex settings. The classic scenario is when one side is manually set, like a switch port is forced to 100 megabits, full duplex, while the client's network card is left on auto-negotiate.
And the negotiation fails.
It often fails to negotiate correctly. The side that's set to auto-negotiate frequently defaults to half-duplex operation.
What's the consequence of that incompatibility?
Yeah.
One side full, one side half.
It's chaos on the wire. The full duplex side just transmits data whenever it wants, assuming it has exclusive use of the wire. But the half-duplex side is using a protocol that means it listens before it talks. So when the full duplex side just starts blasting data, the half-duplex side detects collisions constantly.
And that causes errors.
Massive, non-stop data link errors and discards. The system throws away the corrupted data and immediately triggers that painful TCP retransmission mechanism over and over again. The network looks like it's working, you have a link light, you can ping it, but your backup speed is just agonizingly slow and intermittent.
So what's the key troubleshooting tip to spot this invisible error?
You have to use command line tools. Use the netstat command. If you run netstat-e on Windows or netstat-ai on Linux, you're looking at the interface statistics for trouble. If you see a high and continually rising count of discards, errors, or collisions, that is a huge red flag. It tells you there's a physical link problem, and a duplex mismatch is very often the hidden cause.
Finally, let's factor in the performance cost of encryption and compression overhead, particularly when it happens on the client.
Both software encryption and software compression, when they're done on the backup client, are extremely CPU and memory intensive. Encryption especially requires a ton of computational power for the cryptographic operations. This processing overhead will definitely impact the client's ability to maintain a high data rate.
Is that performance hit always worth the benefit?
It really depends on your main constraint. If you're sending data over a narrow, bandwidth-limited WAN pipe, like from a remote office, the massive benefit of shrinking the data volume by 80% with compression often outweighs the CPU cost.
So you're trading local CPU cycles to save expensive network bandwidth.
Exactly. But if your network is 10 GBPs and your client CPU is already pegged at 95%, the last thing you want to do is add software compression.
And there's a crucial warning in the sources about compression.
This is non-negotiable. You should never perform software compression on data that's being sent to a storage device that already performs hardware compression. The classic example is a tape drive.
Why not?
Tape drives rely on seeing raw, uncompressed, repetitive data to achieve their high reduction ratios. If you send them pre-compressed data, which looks random, you waste CPU resources on the client, and then the tape drive can't achieve any additional compression. It's a lose-lose scenario, high cost on the client, no benefit on the storage.
We have covered a lot of ground today, really dissecting the messy realities of client-side data protection.
We have. We moved way beyond just theoretical design to focus on the precision of balancing resources. I think it's clear that successful backup management means deeply understanding the unique I/O demands of small files, using parallelism with multi-streaming, mitigating the nightmare of remote sites and time zones, and critically being able to diagnose those subtle but devastating network issues like a duplex mismatch.
The sources really confirm what we suspected all along. The sheer, overwhelming heterogeneity of client environments is the primary bottleneck. From specialized database agents to laptops that are never online. You just can't solve this by throwing more disk capacity at the problem.
No, it requires deliberate planning, rigorous standardization and segmentation, and a deep practical understanding of how to align everything with your RPO and RTO to protect data in the real world.
It demands an ability to look at a 10 gigabit network connection that's performing like a 10 megabit one and immediately recognize the signs of a protocol issue, not a hardware failure.
Exactly.
Now, here's a final provocative thought for you to carry forward with you. We know from industry data that the vast majority of file restores, we're talking upwards of 90%, are requested within the first 5 to 10 days after that data was backed up. So given the incredible expense, the complexity, and all the resources required for long-term retention managing compliance for years, shipping tapes off-site, data migrations, how does knowing that statistic change the way you would prioritize the speed and reliability of your immediate operational recovery strategy versus your off-site disaster recovery and compliance strategy? Where should your budget truly be focused?
Until next time, keep digging deeper.